Hello everybody, in this lecture we will be solving 1995 IMO problem number 2. Here's a view of this problem. A, B, C are positive real numbers such that they satisfy this condition, and we would like to show that this inequality holds for A, B, C real numbers. Okay, so I will start with a substitution because these terms, these cubic terms in the denominator are quite annoying. So replace A with 1 over x, basically, B with 1 over y, and C with 1 over z. Let's start with the condition here. The condition is replaced by 1 over x times 1 over y times 1 over z, which is still equal to 1, implying that x times y times z is equal to 1. Notice that if I apply, for instance, AMGM on the following expression, x plus y plus z over 3 is obviously greater than or equal to the cubic root of xyz, but xyz is equal to 1, so that's just equal to 1, implying that x plus y plus z is greater than or equal to 3. I'll make use of it in a minute, but going back to our expressions, let's focus on one of them. So replace a with 1 over x now, cubed, 1 over y plus 1 over z. Now if I rearrange it carefully, I get the x cubed goes to the numerator, then I will have a y plus z here divided by yz, which is equal to x cubed yz over y plus z. But recall that xyz was equal to 1, so as a result all that we're left with is this nice expression. So therefore the inequality that we would like to prove reduces to the following form. Basically it becomes x squared over y plus z plus y squared over z plus x plus z squared over x plus y is greater than or equal to 3/2. Now I will make use of this observation that I made earlier to replace this 3 here with something bigger. So as a result, I claim that proving this new result, namely x squared over y plus z, y squared over z plus x, and z squared over x plus y being greater than or equal to 1/2 x plus y plus z is sufficient, because if this inequality is true, if this 2-star inequality is true, because x plus y plus z is greater than or equal to 3, that gives us back the result that we want to show. So as a result, I will be proving instead this form, which is stronger. If we can show this, it will automatically imply the desired result. Okay, so for this I will make use of Cauchy-Schwarz theorem. Let me just remind you the more common form like this: a2 squared plus 4an squared times b1 squared all the way to bn squared. That thing is greater than or equal to a1 b1 plus a2 b2 plus an bn squared. Now the way I will be using the Cauchy-Schwarz will be with n is equal to 3, and I will set for a1, a2 and a3, I will set them as for a1 I will set it as square root y plus z. For a2 I will replace it with z plus x, and for a3 I will be replacing it with x plus y. For b1, b2 and b3 I will replace each with x over a1 basically, but a1 is just square root y plus z, but okay, let's just write it like that. So y over a2 and z over a3. Now if you plug in these expressions onto this Cauchy-Schwarz inequality here that we described earlier, then we would get the following. So a1 squared will be just simply y plus z, a2 squared is simply z plus x, plus, and a3 squared is x plus y. times, so b1 squared is just x squared over a1 squared is just y plus z, so therefore sorry for that, x squared over y plus z plus, and similarly b2 squared is just y squared over a2 is just square, so z plus x, and finally z squared over a3 is square root of x plus y when we square it, so all we will be left is x plus y. So that expression is greater than or equal to, now the nice thing, so when I multiply them side by side, the a1s will cancel out, so all I'm left is an x here plus an a2 b2. When I multiply them, all I will be left with is a y, and finally a3 b3 is just a z squared. So it is the same as the result that I want to prove, right? So why is that? Because look at this expression here. This is just 2 times x plus y plus z here, and so therefore they will cancel out, right? So if I do that, so this side here will cancel with the square here, and as a result, comparing these two expressions, this expression here, all I will be doing is to take the 2 to the other side. It will go as 1/2, and boom, and we will be done. So that solves basically the problem. So that was a rather easy IMO problem, I think, for a number 2 at least. An alternative way, which is also pretty beautiful, is once you again, if what we want to prove is this result, after assuming I did already the substitution, in fact we could solve this using convex functions, and namely Jensen inequality. So let me write down this this thing that we would like to prove one more time, and let's see if we can find some functions. So we want to show that x squared over y plus z plus y squared over z plus x plus z squared over x plus y is greater than or equal to x. Let me see if I can get this one directly. Yeah, okay, so the function that obviously makes a lot of sense to think about will be so something similar to this. I will make the following change though. So if you consider the following function f of t equal to t squared, and this is the trick, divided by x plus y plus z minus t, so the sum minus t, so the sum, let's call it just s minus t, where s is equal to x plus y plus z. Now consider this function. So this function, well, we need to first identify if it's convex or not, and so on. So we need to take basically the derivative. So this is kind of like a calculus proof. I'm sorry for that. So if you take the derivative of this function, it comes out as the derivative of a fraction, which is s minus t squared here, and then we'll take the derivative of the numerator, which is 2t times the denominator, minus the derivative of the denominator times the numerator. The derivative of the denominator is minus 1, minus 1 is a plus, times plus t squared. But then the nice thing is, if you rewrite this in the following form, s minus t, that's a minus sign, minus 1, oops, if you don't want to use the second derivative basically, but if you already started it, you can, well, even use the one more derivative, so that's not a big deal either. But if you do this, minus 1, oops, sorry for that, squared, you just realize that this expression is increasing in the variable t, right? So because if I increase t, the denominator gets smaller, and the numerator, the whole ratio increase, and the same thing here. So therefore this function is an increasing function in t. So therefore what I'm trying to say is the second derivative is positive, and as a result you have a convex function. So a convex function like, so like something like that. But then for the convex function, the Jensen inequality, so just just as a reminder, so if you have x and y here, this is f of x here, you have f of y, right, okay, then the expectation is here, yeah, so this is the average basically when I say the expectation. Yeah, let me just write it as an average here, x plus y over 2. So when you look at the value, so you have these two numbers here. So this one is let me write it here, f of x plus y over 2, which is obviously greater than this guy, which is just the regular average, which is f of x plus f of y over 2. But then I just realized that if the second derivative is increasing, it means oh my goodness, yeah, the function is looking upward. Yeah. The second derivative positive means, oh my goodness, so it's convex up or concave up, so it's convex function, not concave down like the way I did here, right? So sorry for that. So let me just rewrite this. Sorry. Okay, so but you get the morals of the whole thing. So basically my function looks like that. So so it's increasing at an increasing rate in that sense. Okay, so let's just redo it. So if this point is A, this point is B, so you have the expectation here, and then oops, this point here is f of A, this point here is f of B. Well, the regular, so you have these 2 points here, so the regular average, so this is the expectation of f of x. So that guy is greater than f of the expectation of x. Okay, so that looks good. So therefore, long story short, what I'm trying to say is that f of x, so the left hand side, f of x plus f of y plus f of z turns out to be over 3 is greater than or equal to f of so f of x plus y plus z over 3, like that. Okay, good. Oh, that was such a okay. So but x plus y plus z, we decided to call it as s, so that's simply equal to f of s over 3 now. Okay, so if you and we can actually move the 3 to the other side, so that would explain the 3 on this 3 here. Plugging into this function, we get x squared over s minus x plus y squared over s minus y plus z squared over s minus z. And let me move that 3 to the other side. This is greater than or equal to 3 times. So f of s over 3. So if I plug in s over 3 in this function, so I get s over 3 squared over s minus s over 3, which is equal to 3 times s squared over 9, right? So 2s over 3, yeah, so the 9 and the 3's cancel out. So I have, so the square and the s cancels out. So is that s over 2 here? So I have, oh, right. So I just got s over 2, which is actually even better. Yeah. So yeah, it is just this form. Yeah, the stronger form. Yeah. So therefore, I just proved this one. Again, using just convexity and Jensen inequality, basically. But as I said, there's quite a few different ways you can solve this problem, which is, as I said, a pretty easy question for an inequality problem at the IMO, at least as a problem number 2 here. That solves the problem. Hope you enjoyed it, and I'll see you in our next video.